everyone. In this video I'm gonna talk about attention, and I'm not just only talk about the simple attention that is in attention is all you need, but also I will try to talk about other types of attention as well, like sliding window attention and dilated attention and so on and so forth. So yeah, let's get into it. So first of all, why do we need even attention? So the reason is so other recurrent models. So when we want to process a sequence, we need to know that how much in the past or in the, let's say, previous tokens we need to pay attention, and how much each token we need to pay attention to. What's the measure, what's the amount of attention that we need to have to each of the previous tokens. So the problem with RNNs is that they are not very good at it, and also at the same time, because they are kind of autoregressive models, so they are not really good at what's that, training and GPU usage. So we need another bit architecture or building block, which is called attention, and this paper has been published on, I guess, 2017 by Google, by Wiswani. In fact, that's one of the writers. And yeah, let's just literally and quickly get into it. I'm not gonna go to the whole paper, but I'm gonna just explain quickly the mathematics, and then I'm gonna show you the code and some demos of it. So technically what I'm going to focus on today is this little part over here, which is multi-head attention. And yeah, but let's first see that what is the, in fact, the scale dot product attention. So the thing is, when we have so the Q, K, and V, they stand for query, key, and value, and we will see them what are they in a minute. So the way that we simply calculate attention is we simply multiply the Q to transpose of the K, and then we divide it by the square root of the D of the K, or we call it D model, and then we take a softmax out of it, and then we literally multiply it by V. And what D of the K is just simply dimensionality of the each of these tensors technically. But how do they look in real life? So you can find everything in my GitHub. I put all the code and demos right there. And in terms of demo, so imagine that we have this sentence. So the sentence is: the lazy dog wore sunglasses, stole my sandwich, barked at the fridge, then blamed the confused cat for everything suspiciously. So imagine this is our sentence, and for simplicity, imagine that each of the words are tokens. So technically we have the total of 21 tokens, and we do count this start of the sentence as well. So, and also at the same time, imagine the dimensionality of the embedding is equal to 8. So that dimensionality, as I mentioned here, is exactly this D of the K, so which is technically embedding here. So what happens, we imagine that we put all these words or tokens into an embedding, and we got these tensors for each of these words. So how this embedding matrix looks like, so it would be a matrix of tokens by D model, and tokens because we have 21 tokens as you can see here. And the dimensionality is 8. And by the way, these numbers are mainly made up. These are not real, just for demonstration purposes. So yeah, now imagine that we have the embedding matrix, and this matrix is tokens by D model dimension. So what we do next, as you can see here, what are we trying to do is we're trying to calculate the amount of attention or attention scores for that matrix or for that sentence. So in reality, in the codes, what we have, we will calculate or initialize some weights for each of the q, k, and value, and these weights are just simply, as you can see, the technically the dimensionality of them. As you can see, it is d model by d model, which is here it is 8 by 8, and these are learnable parameters which technically help us to learn what are the sentences, what are the tokens, where to attend, and so on and so forth. So technically these are the parameters and learning parameters that will help us during the training to understand better and more about the sentences and tokens and relation and I don't know, long-term frequency, so on and so forth. So what we do technically in the code is we initialize 3 of these matrices for each of the q, k, and value, and what we next do, we multiply them by, as you can see here, to our embedding, and this is technically the the matrix that we get. Again, remember that our embedding and embedding matrix was tokens times d model. The weights are d model by d model, so technically the queries keys and values after multiplication by weights would be tokens times dk or d model, and these are technically the matrices that we get. And again, I emphasize that these are all available on my GitHub. You can go there and have a look. Then what we do is we technically try to get the similarity score, and where is that? It is q times transpose of the k. And again, if we go back, we can see that both of them, this q and k, they are matrices of token by d of the k. So if we transpose k, that would be d of the k by tokens. So if we multiply them, we have tokens by tokens dimensionality, as you can see right here. So it will give us a kind of rough estimation, not completely, but rough estimation of, for example, okay, the second token, which is the, how much it attends to other tokens, how much it pays attention to other tokens. For example, the pays attention, I don't know, this amount to this token. And by the way, these are the numbers. As I said, these are not reality. We need to do the softmax, then we can literally say what is the probability that they all sum up to 1. So here, imagine that the amount that the pays attention to the start of the sentence is 0.33. It pays attention to itself 0.64, and so on and so forth. And then what we do, again, back to the equation, we divide it by d of the k. In our case, it is 8. So we need to divide it by the square root of 8, and this would be again the matrix that we get. And finally we get the softmax out of it, and softmax can tells us that, okay, what is exactly, it kind of aligns or unifies the rows. So for example, I can say that, okay, d pays attentions 4% to the start of the sentence, 4% to the itself, 4% to the second or third token, 5% to fourth token, and so on and so forth, and they all sum up into 1. So this part is technically, we've calculated the whole this part, and then what we do is we simply multiply that into v. So this is the attention weights that we got. We multiply that by v, the values, and then what we get is simply the output and the technically the last score that we have. But I would like mainly concentrate on here. So as you can see, the problem is with this attention is once we calculate the whole attention and how much each token attends itself or to other tokens. So the problem is, for example, in the case of this method would tell us that how much it attends to all other tokens within that sentence, which is technically not the best, because you know that, for example, in the large language models, we might have a really big sequence, and imagine when we want to calculate the attention for that. So that would be really hard and I don't know, memory consuming, because we have long sequences, and if you want to calculate the whole attention with this method, which is technically the complexity is n squared, is not very efficient. So that's why we do have other types of attentions as well, which would help us to reduce the complexity and memory usage. So what are those types? So if we say this is the full attention, which each token attends all other tokens within a sequence, so we have something called the sliding window attention, which each token only attends to a sliding window of nearby tokens. For example, let's say if it is 3 tokens, it will only pay attention to the next and the previous 3 tokens, as you can see in this pattern. Or we have dilated sliding window attention, which is technically the same as a sliding window attention, but it has holes in it. So some tokens are on and off. And also we have global sliding window attention, which as you can see in this image, it is somehow the combination of full and dilate and a sliding window attention. But how it looks like in our demo, so you can go back here and say I want a sliding window attention, and as you can see here, this is how it looks like in our sliding window attention. So as you can see here, for example, the word the only pays attention to the start of the sentence, to the word the lazy dog wore, and that's all it pays attention to. Or for example, this one, this my only pays attention, if I can find it, it would be the columns in fact of 8, 9, 10 and 3 before that, which is 6, 5, 4. And this one in this example, a sliding window is 3. So if we, for example, make it 2, it would be less. If we make it 1, it would look like this, and so on and so forth. But let's go back to 3. And also, so it is just, as you can see, we don't need to calculate all of the in fact positions. It's been reduced, and it is much better in terms of complexity and memory usage. For the other one, which is dilated, the sliding window, as you can see, it has holes in it. Some of them are on and off, which again will help us. And also there is another variant of it, which you can literally say these tokens are also on and off. So as you can see, this example is somehow the combination of dilated and the sliding window, but you can literally make any type of it depending on how optimized you want it to be. And also something that I forgot to say, that the sliding window attention is very popular. For example, many of the current and new LLMs, they use it, like Mistral, like Llama, and so on and so forth. And yeah, and the last one, which is global attention, as you can see, the first tokens technically they can attend all other tokens, and the intermediate tokens they can attend only that sliding window, those tokens that are available in their sliding window in fact place. So the one question that arises is that, okay, in the full attention, each token pays attention to all other tokens and it has understanding all of rest of the sentence. So how a sliding window can't do that? So the thing is, I have a full explanation in this video and I will put that video in the description. You can go and have a look. I will very quickly explain it here. So when we have multiple layers in our transformer architecture, so imagine if we say that, okay, in the first layer, for example, the first token attends the lazy and the dog. So the first token in the next layer has information about all these three, okay, or four. So that's the first token. It has information about the three or four, three next tokens and three previous tokens. So in the next layer, and also that's also valid for the rest of the tokens. So the next layer, when we say that, okay, when we want to again calculate the sliding window attention, so we expound at that receptive field. For the next layer, we will have more understanding of the context. So that would be something around, I think, 9 tokens or 6 tokens for the next layer. So that's how technically it works. And by adding more layers in our technically transformer architecture, we can make sure that we have a full understanding of the whole context. And again, as I said, you can look at and check this video for more information. And yeah, so technically that's how it works and how it is. And let's just quickly go to the code and see how we can write it down. I will quickly show that how we can write the multi-head attention, and yeah, let's just start it. So what we do, we technically start by importing a couple of packages, and what I will do here, I will try to write it in PyTorch, which is technically more it's more popular in this field. So what I first do is I import torch, and then I import torch.nn as nn for the layers and neural net. I can add torch.nn.functional as if for Softmax and others. Oops. And then I can add tensor for from torch for the types and d types. And finally I add a couple of typings. I import optional and tuple. Okay, so what I will first do, I will first try to write this down, which we can somehow call it scale.product attention, and then I will go back to multi-head attention and how I will make a class for that one. So first I'm gonna write a function for scale.product or scale.attention, and we can start it with scale, let's say dot attention, and what it accepts as input, as you know, and as you can see here, it has q, k, and v, and each of them are tensors of the type tensor. And also what we can add as well is the mask, and I will explain what is mask in a minute, but this one is technically optional and it shouldn't necessarily be there. And again, it's a tensor as well. We put the default as none, and what it will output is, again, as you remember, it is a just simply tensors. But what we usually do is we usually keep the scores and output separate, and we try to output both of them. So that would be a tuple of two tensors, a tensor and tensor. So what is this mask? So if you look at here, and let's go back to self-attention. So the thing is, when we want to, specifically in large language models, when we want to generate, let's say, tokens, so the thing is, the LLM should not see the future token. So imagine if I'm right here up until war. Imagine the sentence is the lazy dog war, and I want the LLM to complete the rest of the sentence. So it doesn't make sense that it can see the rest of the sentence when we want to do the training. So we need to put a mask to avoid LLM to see what's in the what's the rest of the sentence technically. So we put a mask and we try to make them all 0, and by that we can make sure that okay, this LLM cannot see the future tokens, and it can we are confident that it can learn from our data. So this mask is exactly for that reason. So about Q, K, and V, just quickly explaining that how do they look. I can quickly just write some notes here. So those are technically tensors of the shape B, T, or we can call it this as well, H and D. But what are they? So they are batch size, the sequence length, number of the heads, and the dimension of each head. Again, quickly explain what heads mean, going back to the attention itself. So you saw here that how we calculate the in fact attention, and how we did the multiplication, so on and so forth, and when we had this embedding, for example. But in reality, the embedding could be much bigger. So for example, in the case of Mistral, it is or Llama, it is, I guess, 4096, which is much bigger. So it would be great if we can find a way that we can parallelize or make the calculation much faster. So the way that we can do it is we can break each of these tensors into smaller pieces. So imagine we have 8 here. What I can do, I can break it into 4 tensors of the size 2. So this would be the first one, the second one, third, and the fourth one. And what I can do, I can separately give them to different weights. So I will have different weights for each of those heads, and then I can do the rest of the calculation. So demonstration, in fact the visual demonstration of that would be something like this. So as you can see, we have QKV, we can break them, and we can, instead of doing all at one, we can break them and give them into different heads. What it can do is technically it will help us an attention to attend different parts of the sentence or embedding, which is much better. And also, as you can see here, it is much easier to parallelize it on GPUs. And what we do, we have two parts, additional parts. We break the tensor, and then we concatenate it. So yeah, we break it and split it and then concatenate it. And so that's why we have these heads and the head dimension here. Okay, so what I need to have is I need to have the model, if you remember from here again, which is, as we saw here, it is the very last place in the tensor. So the model would be, let's say, any of them, q, the size of it, the very last position of it. So now what we need to do, we need to find the scores. And what was that? It was multiplying q times transpose of the k. So, but there is a small hack here, which I will explain it in a minute. And by the way, this at sign is a matrix multiplication in PyTorch. K dot transpose. But when we do the transpose, what we should and how we should do the transpose, because as we know, this is the whole tensor, and which parts and which technically position or indices we need to transpose. So batch size and sequence length, we don't really care about them, and all we need to have and we care about is this number of the heads and head dimension. So technically what we need to do is we need to just say the last one and the one before that, just do the transposition transpose with respect to them. And then what we had the division by the model, so which is torch dot sqrt for its square root, and we can say torch dot tensor. And the reason that we do the torch dot center tensor is because the model is literally a number, could be an integer. We need to turn it into the tensor in order to make all data types unified. And we usually, so this really depends on you, that how would you like to have the d type. So what we do here is we do torch dot float of let's say 32, but it depends on you and how much precision you want to have. And mask, so if mask isn't none, so if we have the mask, what we do is we just if you remember again, so the mask, by the way, don't forget that the mask itself is a matrix, or it's a tensor, and all we need to do is we need to use a torch function called masked fill. And what it does, it will literally fill all the positions, for example in the mask, in the mask tensor, we will have position 0, for example, which we want to technically hide it from the attention. We can put 0 and it will check that. If it is 0, it will put minus infinity into that, and the reason for that is when it goes to softmax, it will literally turn into 0. So if we have mask, if the mask is not known, So scores would be scores dot mass fill if any of the entries in the mask is equal to 0. What it needs to do is turn it into float minus infinity, and that's technically how you write a minus infinity in Torch. And yeah, then what we need to do, so up until now we made this part of the equation within the parentheses. We now need to do the softmax and then just simple multiplication, matrix multiplication to we. So let's just get into it. So we have the scores again, and all we need to do is, if you remember, we imported this f from functional nn.functional. What we need to do is f dot softmax is in that part of the package. Softmax, we give the scores and we give it with respect to dimension equal to -1, which is technically the last part of the tensors. And what we do as the output, the last part is scores let me just check to okay, score at we, and that's it technically. And we can return both output, or let's say out, yeah, and scores or a score. So this was literally the first part, which was the attention or scale.product attention. But how we can make the multi-head attention? So technically this bit of the transformer architecture, so we can write a class for it, and we can technically call it multi-head attention. So let's get into that. Multi-head attention, and because it's a layer, so it literally inherits from nn.module. So let's initialize it. So what are the inputs to this? So we have the self, the model, and number of heads. So technically that's all we need, and we will see them in a minute, that what are we going to do with them. And both of the model and number of head, they are of type integers. So we have number of head, which is again int, and let's say super init, and yeah, that's it. And yeah, let's initialize and define some of the parameters here. So the first thing is, so as we had here, so imagine that, okay, I want to have, for example, a specific number of hits with a certain the model. So the first thing is, when I have, I don't know, for example, let's say the model of 8, when I want to break it into whatever number of hits that I want, so the dimension of each head times the number of heads, so technically they should add up and sum up to the original D model. So what we can do here is we need to put a assert to make sure that it works. So D model, whether it is number of head is equal to 0, if not, So just print out the model must be visible by number of heads. And yeah, now let's just add some values here. We can say self dot the model, which is going to be the model, self dot number of heads, which is again going to be number of heads. So we have the dimensionality of each head, which is self dot head dim, which we can say it is the model divided by number of head. And then if you remember here, right here, back here, we had weights for each of k, q, and value. We need to set them up, and the way that we set them up is we have self and we have it for q, k value, and also it's common that we put it into the output as well, so the model can learn as much as possible. So we have self, and we call them usually projection, self that q proj, and it is nn dot linear, I think it's linear, and the dimensionality of it, as you remember, it's d model by d model. So I can just copy this a couple of times. I can turn this into q, k value, and the output for the output, and you will see this one in a minute. Okay, if you remember again back into this diagram, what we said we have the embedding, we will break it, we will split it into the heads, and then we do this dot product, and then we will concatenate them all. So we split and then we concatenate. So right now here I'm gonna write the split heads and combine heads function. So let's get into that, and since we use them in the class, we put on the line split heads, which technically as an input it will literally take a tensor, and that's all, and any kind of tensor with the type tensor, and what it gives back is again a type of tensor. So remember that back here we had the batch size, but now because we are in each batch, so each of these tensors, how do they look is they are the form of batch size, number of heads, and technically what's that, the head dimension. So what I can do here is I can just take that size, I'm gonna split the size, and I can say x dot size is equal of the x. So this is how it looks, byte size, the sequence length, and what was that, the head diamond, the number of hits, and then I can say x is equal x dot view. All I need to do here is I literally need to what's that, I want to change the view of it. Why? Because I want to split them into different heads and number of heads. And sorry, I think here I said head dimension and the model. No, it is byte size, sequence length, and the dimension. So what I want to do is I want to break this dimension into number of heads and head dimension. That's what I want to do. So we have the full tensor here, back to here. We have, let's say, this embedding within a batch and sequence length is. I want to break it into whatever the user specifies. So I want to view it as bt self dot head dim effects number of heads, sorry, and self dot head dim, and then I will return x dot, and the reason for this permutation, I will do a permutation and I will explain in a minute. It is 0, 2, 1, 3. Okay, the reason for this is technically, as you can see, so what we did here is we literally kept the first one, the batch size, and what we did was we literally permuted the sequence length right here with number of heads. Why we're doing that? Because when we want to do the multiplication and the scale dot product, we need to have it in that way. This is just the reorganizing the tensor shape, and that's it technically. And once we did the calculation in the scale dot product, we return it back, and you will see that in a minute in the combine function. So we can define the underline combine heads. So again, it will literally take a self and a tensor, and it will give us back a tensor, and I need to put it here. And the way that it works is just literally the other way around of the split. So what do we have? We have, again, if you want to get the size of the and the shape of the, or let's say the shape of the tensor, we have b number of head, t, and head dim. And this combine heads, again, I emphasize, is once we did this scale dot product and we want to concatenate them. So this is how this x dot size will look like. Yeah. And I think I add this. Yeah, I shouldn't do that. And yeah, again, just to finish it, what we need to do is, so here we change the view and then we did the permutation. Right here on the next one we do the permutation and then we change the view technically. So x would be x dot permute again, and it's literally the same thing. Yeah, because we literally want to change the position of the number of hits and sequence length, and we return x dot view of the b t. So here we have number of hits and head dimension. It was from the split heads. Now we want to combine them. So what we need to do is just literally multiply them to each other. So it would be number of heads times head dim, and But now to the forward pass of the multi-head attention. So how that one looks like, which is technically this part within the layer. It would be forward, and what it takes is self. We take the x as a tensor, and we may or may not have the mask. It is optional again, type of tensor. It's usually none, and what it returns is a tensor as well. So now we have that x. What we need to do is we need to, back to here, we have each of those embeddings. Let's say we need to multiply them into the weights and then rest of the scale dot product. But so first we need to multiply them by heads, then multiply them by heads somewhere around here. Yeah, split them, do the scale dot product attention, concatenate them, and then get the result. So how we're going to do that? So let's say we have q. So what we need to do is first we need to do self dot. If you remember, we had this weights here, q proj. So we multiply it by q proj. So this is the weight. Then we need to split it. So what we need to do next is self dot underline, if I can find it, split heads, and that's it technically. And this is technically somehow the what's that, self attention. So that's why we technically have, we will have q, k, and v, all of them would be the same thing as x. So I will just again copy that. So here in this one it would be q, k, and v, and the prods would change, k and v. So what we need to do next is simply we need to perform the scale dot product on them. So we can say scale dot product attention on q, k, and v. And if you remember, we had two outputs, output and the score. You can just simply copy that from there. And then what we will have later on is we can say output would be equal to, so right now we have the splitted version of them, but we need to combine them back, and as I said, then we need to multiply them by this weight as well. So we need to return them back now. So what we need to do is we do self dot underline combine heads, which is technically the out, and then we can multiply them by the self dot out projection, and then we can return the output. So this is technically all this code is technically for this and this is the scale dot product and the multi-head attention, and this is a very tiny bit of the whole transformer layer right here in the multi-head attention. And yeah, that's it for this video, and I hope this was informative for you. Let me know if you want to explain the whole architecture in the comments, and so on and so forth. And also don't forget, if you want to learn more about the how we can maintain the context in the sliding window type, you can just check out the video in the comment in the description. And yeah, thank you very much.